also start recording separately just in case I mess up and need to cut things up. But yeah, so we're going to be talking about homework 9, the medium questions. And yeah, I've been thinking a little bit about just logistically if it would make more sense to like copy and paste the statement of the problem into these things. But I don't know, maybe that's too much work. So
I mean, yeah, it's that's all you. So I mean,
yeah, I guess I'm just thinking out loud.
Yeah.
But yeah, okay. So for now, we'll forego it and see if it makes more sense in the future. But okay, so it's a 12 kg automobile is at rest in a traffic signal, or 12,000 or whatever. So okay, basically the idea is, you know what? Let me actually hold on a second. Let me do. All right, so all right, starting recording for real this time. So we're covering the homework 9 medium and maybe hard questions. But the idea is, all right, so we're at a traffic signal, right? So we have one car over here that's initially at rest, and we have like a truck that has some constant speed. So I guess if we call this V of the truck, and this is, well, the car has an acceleration, but no initial speed. And the question is basically asking us, what is the center of mass at some particular time? And what is the speed of the center of mass of the automobile truck system? Okay, so I'm going to do this without using specific numbers for the most part. But if this is the mass of the car and this is the mass of the truck, if I remember correctly, x of the center of mass is just going to be mass of the car times x of the car plus mass of the truck times x of the truck divided by the total mass, right? I hope I have not misremembered this. Seem good?
Yes.
So the only issue here is that x of the car and x of the truck are functions of t. So let's rewrite this as xcom is a function of t. And maybe rewrite these also as functions of t, which means that, you can come up with an expression for them. And moreover, you can take the derivative and cute stuff like that. So the little t is time, the big T is truck, just not to get that mixed up. But the point of this problem is basically saying, all right, if we have this expression, we just need to figure out what xc of t are. This is basically just putting together a couple things that you know from kinematics as well, and folding them in to the center of mass problem. So xc of the truck, right? Something that has no initial velocity, but does have an acceleration. Does one particular kinematic equation come to mind, or do you remember what the expression for that is? Right? It's v naught t, which is again 0, plus 1/2 at squared. Seem familiar?
Oh yeah.
Exactly, right. This is just one of those things where things that you totally already know, like if I only asked you this part of the problem, I think everybody could do it. But seeing it in the context of something else might just take a moment to jog your memory. But as for the truck, I think it told us that it's a constant speed, right? So this is just going to be v of the truck times time. So now at this point, you have two perfectly good expressions for xc of t and xt of t. So you basically just plug them in, right? You basically just go ahead and plug these expressions in. And then that'll get you the center of mass at any given time t. So then you just plug in a value of little t that you like. And if you're being asked to find the speed of the center of mass for the automobile truck system, well, then you just, taking this as a function, you just take the derivative with respect to time, right? Because if you want v of center of mass, that's just equal to ddt of x center of mass. Make sense?
Yes.
Yeah. And as always, when it comes to calculus, make sure to take the derivatives first before plugging in t values, because otherwise you're going to find that everything just comes out to 0. Yeah, that's a mistake that people frequently make when they're relatively new to calculus, but you plug things in at the very end, right? At the very, very end. Don't just make sure to take derivatives first if you're going to take a derivative. Okay, so far so good.
So far, so good.
Okay, making decent time. 4 minutes a problem. Let's see if we can keep this up. Okay, so number 2, we got a little dog. That's okay. So if this is shore, right? We got a boat, and on this boat we have a dog. That's, I guess, distance d. Okay, so what's up?
No, I didn't say anything.
Okay, so we know the mass of the dog, we know what d is, and we also know the mass of the boat. Let's call it little b. And okay, so what else do we know? We know that the dog walks 1.9 meters along the boat towards shore and then stops. So what's going on here is if the dog walks a little bit over here, because we're assuming that the water is just like totally still, so there's no external forces acting on the dog or the boat, which is to say that the overall center of mass, because it was originally at rest, can't have moved, right? Because if something's at rest and there's no external force acting on it, it stays at rest. Which is to say that if you treat the like center of mass as an entity, it's saying that the center of mass can't shift at all. So if the dog moves a little bit to the left, then the boat has to move a little bit to the right correspondingly. So the other thing we know is that the dog walks 1.9 meters, or let's call it let's call x of d to be the amount the dog walks, right? Relative to the boat. And you're being asked to find how far the dog is from the shore. Okay? So the idea is x of the dog, right, is going to be like this arrow right here, but that's relative to the boat. So if the dog moves like left by 2 meters, but then the boat moves right by like half a meter, then the dog overall only moves to the left 1.5 meters. Makes sense, right?
Okay, so the dog and the boat are moving independently of each other?
I wouldn't say the word independently. They kind of got to be like in unison, right? Because the idea is there's a center of mass between the system of the dog and the boat has some center of mass. Let's say that it's like kind of right here, right? Center of mass. So the idea is because the center of mass can't change because there's no external force, every time the dog moves a little bit to the left, the boat has to move a little bit to the right to compensate.
Okay.
Right? That's the idea. So I haven't actually solved this problem out myself. In fact, I just sort of looked at it and just got the gist. But let's just write out a couple things, right? XCOM is equal to... so that the reason why I use like center of mass here is because you can kind of try to think about this as momentum, but you don't know exactly how fast the dog is moving or anything to do with time, really. All you can say is there's a net change in the dog, but there's no net change in center of mass. So there's got to be some change in the boat's position, right? But let's give this a shot. Let's say mass of the dog times... okay, you know what? I'm going to... Let's just say that... Okay, I regret saying that earlier when I say xd was equal to like 1.9 or 2 or whatever, let's forget that. Let's just say that x is measured relative to shore, okay? Like x of center of mass measured relative to shore, x of dog relative to shore, and mass of the boat times the center of mass of the boat, which is xb d plus m b. Let me just say a moment. For a lot of center of mass problems, they're made a lot easier if you just go ahead and assume that the boat can be treated as a as a point object, essentially. Which is kind of weird because the dog is walking along it, right? But the idea is for problems like these that aren't too complicated, you can basically approximate the boat as just being the center of mass. Like, you can approximate the boat's center of mass, and just say that, like, this is the mass of the boat, and it's all concentrated at this position, xb. And notably, xb is not necessarily the same as the center of mass of the whole system. Right? Because xb is just for the boat.
Right.
Am I making sense so far?
Yeah.
Right? Because, like, xb, I just wanted to clarify that because xb on its own kind of doesn't make sense because the boat is kind of wide, right? But I'm saying xb stands for the boat's center of mass. as opposed to the whole center of mass. But okay. All right, so far so good. So basically I'm saying X center of mass it does not really change. So like if this is mass of the dog plus mass of the boat, so if this is like initial, right? Let me say mass of the dog I for initial and mass of the boat. Sorry, X dog initial, X boat initial, right? This has got to be equal to almost the exact same equation, but X dog final plus mass boat, X boat final, divided by mass of the dog plus mass of the boat, right? Why did I write 2 plus signs? That's silly of me. So the idea here is that, okay, so first things first, right? Like the XD plus MBs just cancel out because they're both in the denominator. Who cares, right? But
Right.
XDI, XBI, XD, and XBF are all kind of, are all kind of unknowns, right? And what we do know is that, sorry, this should have been a little F sign, right? What we do know is that XDF, let's put it this way, XDI minus XDF is equal to like 2 meters or whatever was given by the problem, right? This is saying the dog is moving. No, I'm sorry. Let me think about how to actually express this. This is what we're trying to find, right? XDI minus XDF. But we're trying to express this. We're trying to express that the dog moves 2 meters along the shore relative to the boat. How do we express that? Let me think. Yeah, but are you kind of following along so far?
Yeah.
Yeah, we just got to think real quick about how to write exactly what we're trying to find, which is, I think, just this thing, right? We're trying to figure out, from the shore's perspective, how far is the... Like we're basically just trying to find this, right? How far is the dog from the shore? And I need to try to express the fact that the dog walks 2 meters along the boat towards the shore. Like, how the hell do I represent that? Yeah, so let me think about what that means. So the dog walks 2 meters, right? So that's like 2 meters plus whatever the change in the boat's movement is equal to its final position. Does that seem right?
Yeah.
Yeah. So let's see. So I think that's saying XDI. Like, I'm basically just trying to come up with another equation that I can sort of mash against this one over here to try to make sense of something. But I think it's saying like X dog of the initial, if it walks to the left by 2, right? And during that process, the boat also shifts to the right by, I'll just call it like delta X of the boat, right? This should be equal to X dog final. I think that makes sense. And the question is, does this give us enough information to solve?
Which it does.
Yeah, I'm staring at it. So we know the mass of the dog, right? We know all the masses. And I'm just going to go ahead and maybe cancel out this denominator because I don't think it's important anymore, because we can just multiply through, right? Can we figure out exactly what XDF is? Which is just this term right here. I'm just trying to figure out what's known and what's unknown. I feel like we have one too many variables, and maybe we need to think of something else.
What if we do, instead of the I and the F, we just use delta?
Yeah, let me think about that real quick. Okay, so then that would basically say, ooh, yeah, I think you're right. So delta x of the dog, I guess that's minus delta x of the dog plus delta x of the boat has got to be equal to 2. So if we keep along this, I think you're right. I think, oh wow, student becomes the teacher moment, right? Because at this point, if we stick to only the deltas, yeah, then we have an equation of 2 unknowns and, well, 2 equations. So yeah, I think that would work just fine. So at this point, we can just sort of combine these, right? This over here turns into md of, if we take this term and subtract this term from it, like just move it to the other side by subtraction, this turns into mass of d times delta x of the dog is equal to mass of the boat times delta
X of the boat.
x of the boat, but there needs to be a negative sign here, right? Yeah, so like what I'm doing is basically just subtracting the left-hand side over to the right-hand side and getting mass of the boat times x of, excuse me, times delta x of the boat is equal to 0. And then I'm just moving this over to the left-hand side. You don't have to if you don't want to. But yes, at this point, we have 2 unknowns and 2 equations, equation 1 and equation 2. So at this point, you should be able to solve, right?
Right.
Yeah. Yeah, sorry that one took so long. Very good suggestion. I was getting confused because I thought I had one too many unknowns, but really just combining them makes everything a little bit simpler. I was a little bit hesitant to combine them because at the end of the day, this is what I want to find. But you're right that simplifying it for a moment is really, really helpful. Because that collapses the number of unknowns. But at this point, once you can find, so, okay, 2 equations, 2 unknowns, not that bad, right? But once you found delta xd and delta xb, I think you should just be able to take this number and subtract it from whatever its initial position is. Or add it to its initial position, rather. And I think you should be good. Make sense?
Yes.
Okay, very good. Very good suggestion. It's good to see you thinking on your feet, too. All right, so next one. So what's happening here is a softball of some given mass and some given velocity at some given angle is coming in towards a bat. So I think this is basically saying if this is the mass right here, and this is angle theta, and it's coming in to meet the, I'm just going to represent the bat as like a square. Doesn't really matter, okay? And then it's basically saying what is the magnitude of the change of momentum of the ball while it is in contact with a bat if it leaves with a velocity of like, okay, so maybe let's call this v naught, and let's maybe say it leaves with some velocity v1 downwards. So the idea here is that it's really not that complicated of a question mathematically, but I think some students got a little bit mixed up as to what exactly they were trying to find, right? So the change in the momentum vector is basically, P final minus P initial, right? So it's basically saying, do this vector subtraction first, and then find the magnitude at the end. Whereas I think some other people were finding the magnitudes first, and then taking the difference, right? So this is basically what we want to find. Do the subtraction first, and then take the magnitudes. I think some other people were doing it this way. You see the difference?
Yeah, because then, yeah.
Yeah. And like one of the really easy ways to see this difference is if a ball's just coming in to a wall and directly outwards, this over here would just be double whatever or just, if it came out with speed v and came out with speed minus v, right? The difference would be 2v, or rather the magnitude of the difference would be 2v, whereas the difference of the magnitudes would just be 0, right? Because the speed is 0 before and the speed is 0 after. So that's an easy way to see what the difference is between what you're being asked here. But yeah, I mean, at that point, the problem should be like, I hope should be really simple, right? But what is it saying? Yeah, so just figure out whatever P initial is, and you're given all this information, right? That's basically M times V naught, and then just break V naught into the X and Y components, really, right? Is equal to Vx I hat plus Vy j hat, and just pay attention to the signs, because I think Vy might be negative, right? And then P final is just equal to M times V1, which I think just happens to be equal to like minus V1. This is just the magnitude of j hat, right? Because we're told that it's going vertically downwards, so the X component is 0. But yeah, this is basically just, once you break it down, it just turns into a simple vector subtraction problem, and then you find the magnitude at the end. Hopefully pretty reasonable.
So far, so good.
Yeah. And then part B is asking something pretty similar. It's just that instead of going straight downwards like before, now it's going, I think, just directly to the left. But the exact same idea. Just do vector subtraction, right? And just be careful with your signs and find the magnitude at the very end. Okay, I think that should be enough for that one. Hopefully it doesn't have some subtlety that I overlooked, but I think we should be fine. Okay, so next one, problem 4. So very interesting. What it's saying is that it's a bunch of balls separated by some time coming in towards a wall, right? And there's some time here. This is, I guess they're calling it TD. So if this is time versus force, time versus force, and they say that this is F max, and what else? This is TD as well. And then the difference between the peaks is called TR, I think. So during each impact, what is the magnitude of the impulse on the wall? All right. This requires me every time to look it up because I forget it every time, but I'm pretty sure impulse is just the derivative of force with respect to time. Sound about right? Yes, that's literally the definition.
Okay.
Yeah, so J is equal to the integral of force with respect to time. And in cases where the force is simple and constant over a period, you can just do integration, just turns into multiplication, right? But because the force is sort of shaped like a triangle, well, that means you gotta find the area under the curve to find the impulse, right? That's what an integral is. It's literally area under the curve of f with respect to t. So yeah, during each impact, what is the magnitude of the impulse? Well, okay, just find the area under the curve. And hopefully that should be easy enough because it's just a triangle, right? Yeah, you know the base and you know the height, so go ham. And now it's saying during each impact, what is the magnitude of the average force on the wall? Okay, so part B, if, area under a curve is equal to J, right? So that you can find from the graph, and you set that equal to force average times the change in the time is basically TD, right? Well, that's just basically asking you to solve for force average. So just divide through and that should take care of that, right?
Simple enough.
Yeah, I agree. Simple enough. So now it's saying during a time interval of many impacts, what is the magnitude of the average force in the wall? Ah, okay, very good. Oh, but let me mention, for a sanity check, I would expect F average to, well, of course, it's got to be somewhere in between 0 and F max, right? But because it's triangle shaped, I would expect it to be a little bit less than halfway. Yeah. I don't know the exact answer off the top of my head, but I would expect it to be closer to 0 than f max. So, okay, now it's basically saying, okay, we're essentially extending us to a larger time interval now, right? So what is this to say? If we drew a graph much more zoomed out, and there's each of these little triangles, it's basically like saying, over the long run, right, what exactly is the impulse per time? Sorry, average force is impulse per time, right? But one of the ways that you might think of this problem is just to set up a limit, like in a really complicated way, try to figure out as t goes to infinity, find an expression for the total area so far and divide that by the total time. But that's a little bit complicated, right? You could do it this way if you wanted to, but let's see if we can figure out this from just like zooming in a little bit. You know what I mean?
Okay.
So whatever that f average is, right, of many of the different areas divided by the total time so far, you can just sort of zoom in on like a typical, what do you call it? Like almost like a representative sample, right? Because the idea is, you know what the time between impacts is. That was, I think, called TR, right? So if you can basically just tell me what the total area is in this time interval and divide that by TR, that's your answer right there. You kind of see what I'm saying? So like questions like these, even though you're being asked what the magnitude is over many impacts, the funny thing, because everything is really nice and regular, you can actually zoom in and just think about one. Am I kind of making sense?
Back it up a little bit. So
Sure.
you find the one triangle and then divide it by TRY.
Yeah. Let me maybe put it this way, okay? Let's say that this was 5 triangles, right? Sorry. Let me be careful. So if there were 5 triangles, right, the total time distance, I think, would only be 4 TR, right? Because 1, 2, 3, 4.
Okay.
Right? And you notice here that on the left triangle, only half of the area is being counted, and on the right triangle, only half the area is being counted, right?
Yeah.
So the total area here is like 4A. Like the total impulse is 4A for this particular time frame. And what you're getting here is that joule over force, or I guess joule over time. So F average is equal to joule over time, right? That's basically just equal to 4A over 4TR. And the 4's kind of cancel out, so all that you're left with is A over TR. Right? And what I'm saying is, okay, you could have done this number with, instead of 4, you could have done it with 10 or 1,000 or 10,000, right? And you're always going to end up, I hope it's reasonably convincing that you're always going to end up with this number A over TR. But
I got it.
The point of this little excursion is basically saying, okay, if basically 1 TR was like this, you know, halfway here to halfway here, right? It's sort of like saying you could have thought about just each of these individual things on their own, because everything is so nice and uniform, really. You could have just thought about the area in this segment, which is just this particular triangle, divided by this particular time, TR. Like you could have thought about like a representative unit rather than having to think about like 4 or 100 of them. You see what I'm saying?
Yeah.
Yeah. Great. That's just the point that I wanted to make. But okay. Okay, you just gotta rewrite whatever area is from your previous expression, right? I think area under the curve and joule are just the same thing. And just plug that into A and divide that by TR, and I think you're golden. What is that? Does this make sense?
I think so.
Okay. Excuse me. Alrighty. So now, interesting problem. We're talking about jumping up before an elevator hits the ground. I've always thought about problems like these, right? Like, if you're falling to your death on an elevator, and you thought like, okay, may as well give things a try, right? Like, and then you try to jump. You can try to think about like whether or not, like, I guess this problem is trying to answer whether or not that might actually work. Because the hope is that if you jump just the right, speed, it kind of cancels out with the impact, and you're, hopefully left unhurt. But okay, let's dig into the actual problem itself. So we're talking about a free fall from some particular height, h, and during the collision at the bottom, a passenger of some mass m is stopped in some time frame on the order of like 5 milliseconds. Assume that there's no rebound. So it's asking, what is the magnitude of the impulse and average force? Okay, so if we remind ourselves of our sort of basic definitions, right? One way to find impulse is equal to the integral of f dt. And another way to think about impulse is just that it's the change in momentum, right? Momentum final minus momentum initial. Funny enough, this delta momentum actually comes from this derivation right here. But when talking about problem solving, it's actually useful to think about separate things, because the change in momentum is really easy to find, right? Because we know the mass and we know the speed from kinematics, right? We can figure out whatever the speed is at this particular moment. Let's maybe call that v. Let's maybe call that v of the elevator. Or, no, let's just call that v naught. Right? We can find this v naught value from kinematics, right? Just using like, I don't know, any of our equations really. Seem reasonable?
Yes.
Yeah. Yeah, think about which kinematic equation to use, but I promise you, this is another one of those situations where you know how to do this. It's just sort of something that you do know being wrapped up in a new kind of problem, and that might make it seem scary. But figure out this v naught just from kinematics, and that should let you figure out what delta p is, right? Because one moment you are coming down with mass m and v naught, and the next moment you are at 0. So your change in momentum is basically just the momentum you had the moment before collision. So now that you know m and v naught, you know this value. Just be careful about your signs, whether it's positive or negative, right? So that right there gives you the impulse. That's how to do part A, right? Just change in momentum is your impulse. Now it's asking for average force during the collision, right? So f dt is basically equal to f average times delta time. And that's this delta time we had over here. So because we know the joule from part A, or not the joules, the impulse from part A, just set that equal to f average times delta t and solve for f average. Simple enough, right?
That's just like the last problem.
Yeah. What was the last problem? I'm starting to forget. The triangle thing, right?
Yeah.
Yeah. So with this problem, they didn't tell us exactly how the force was acting, right? Like maybe the ground is super firm at first and then softens up a little bit towards the end, or maybe the other way around. We don't really care. They're not asking us about, they're not asking us about like the super specific shape of the force graph. In this new problem, they're just asking us to find the average, and we can definitely do that. Okay. So then, what's up?
No, you're good.
Yeah, okay. So then if the passenger were to jump upward with a speed of 5 meters a second, okay, relative to the cab floor just before the cab hits the bottom, what are the magnitude of the impulse and average force, assuming the same stop time? Okay. So now they jump up. Okay, so the person here is going upwards with a tiny bit of velocity relative to the cab, right? So that's basically saying, what is this? So whereas before, delta p was just P final, which was 0, minus P initial, which was just before the crash. Now it's saying that they're jumping right before the cab hits. So I think what that's saying is... Okay, I'm getting a little bit mixed up here, but I think what that's saying is P final is still going to be 0, but P initial is going to be a little bit different because they're jumping, right? Like, whereas before it was just M times V naught. Now P initial for part C is equal to like M times V naught minus V of the jump. And I think it's got to be downwards, because we're assuming that upwards is the positive direction, so downwards is negative. Does this seem reasonable?
Looks good, I think.
Yeah. As always, be careful about your signs. For this particular problem, I'm taking velocities to be positive, and then just enforcing the sign into like in front of them to choose my directions. If you wanted to do everything, you could incorporate the signs into the velocities themselves, but I think it's basically the same problem. It's just that they're jumping upwards, which kind of like eats away at some of the magnitude of the momentum they have just before the crash. But it's saying that the delta t is exactly the same. And I think P final is going to be the same as well, because they're saying that I assume they'll stop over the same time frame, right? So it's basically saying just do what you did before, find the joules using the delta P, and then find the average force. And yeah. And I think what we're seeing from this is that if the... I don't know what speed the elevator is coming down at. I mean, you can find it from kinematics, but I just don't know off the top of my head. But what this is basically saying is if the person's jumping up with V of the jump is equal to 5 meters per second, if this magnitude is very similar to V naught, then the person might actually be safe because there's not a ton of momentum transfer. But if it's very small compared to V naught, then you're probably screwed, right? Because if you're crashing with like, you know, if 100% of the crash is, you know, gonna toast you, and jumping upwards brings it down to like 90%, you're probably still in pretty bad shape, right?
Yeah, so this one's probably not going to make it.
Honestly, I don't know off the top of my head. It all depends on the magnitude of V naught compared to VJ. But for problems like these that are kind of motivated with some sort of physical meaning, it's always good to think about, like, what's the spirit of the problem here? Does the person get hurt with a lot of impulse? Or do they actually make it off relatively light with little impulse and average force? Anyways, it's just fun food for thought, right?
Also,
What's up?
for the kinematics thing, I got like answers for like I used 3 different equations and I got different answers for each of them. I don't know which one I should be using.
Oh, you got 3. Oh, sure, we can talk. By the way, just letting you know, we are recording. Yeah. So you're saying that in the process of finding V naught, right? You got 3 different answers?
Using 3 different kinematics equations.
Well, clearly something must be wrong, right? Let me guess. Did you happen to use this T inside the kinematic equation?
Yes.
This T is something totally else.
No, I used that. Wait, really?
This T is basically saying from the time you like make contact to the time you like compress against the floor. This T is talking. Yeah. This T is talking about like a bunch of microscopic processes that happen, in that like just in the time of the collision. But this time coming downwards is a totally different time.
Oh,
right.
Okay.
Like this could be like 1,000 feet above, right? And that's going to take a lot longer than 5 milliseconds to fall.
Yeah. Okay.
Exactly.
Just making sure.
Yeah.
Okay, so the one that I didn't use the time for it should be the right one. Okay.
Yeah. If I was using the kinematic equation, right, I would say V naught squared is equal to 2a delta x, right?
Oh, y. Oh, yeah.
Sure, whatever. You know, it's
that one.
Yeah. And the notation here is kind of bad because this V naught is actually the velocity at the end of the falling phase. Like usually you see VF squared minus V naught squared, right? But the velocity initial is 0 because at the top it's at rest. And at the bottom we're calling it V naught, so just keep that in mind.
Oh, okay.
Yeah. Hope that answers the question.
Yeah, thank you.
Very good. All right. Well, feel free to stick around, or if that was your only question, feel free to work on whatever you got to work on. But we'll just keep moving. Okie dokie. We're making okay-ish time. I should have. Okay. So now I think it's talking about the flying circus of physics. Yeah, what the heck is this? This is crazy. So they're like jumping upwards, and then they sort of like drop a sandbag, or in fact, they throw it backwards, maybe, so that they get like an extra boost. That's awesome. That makes total sense, but I've never heard of the sport before. So okay, what's happening here? They're basically asking that we land at liftoff level. What distance would the use of the halteres add to his range? Okay, got it. Okay, so it's basically saying that there's two situations here. One where the person, jumps upwards and lands like a regular kinematic problem. And you can totally find that just because you're told V naught, or I guess they're just calling it V. And their mass as well, right? So under regular kinematics, you can just find the distance they move. Right? Just figure out when using, this is just like delta y is equal to 0 is equal to Vy t minus 1/2 gt squared, right? This equation will let you find t, and then delta x is just equal to Vxt. Yeah? So this is the regular version of the problem, and they're saying that now they have a bunch of sandbags, or whatever they're called, so that when they go upwards, at the height, I think it's saying at the height of their jump, throw them horizontally to the rear at its maximum height, so that their horizontal velocity is 0 relative to ground level. Now, it's saying that they're throwing the sandbags backwards, and therefore they get a bit of a forward boost, right? Because of conservation of momentum. So now they might land a little bit further. And they're basically asking you to figure out the distance between the original scenario and the new scenario. Does the problem make sense? What it's asking you to do?
Yeah.
Okay. Let's figure out what you actually need to solve this problem. So what do we know? We do know the mass of the... What are they calling it? They're calling it a...
Haltere?
Haltere? Yeah. Mass of the haltere is like 5 kilograms or something like that. And the velocity with or without the halteres is the same. So what else do we need to know? He throws them horizontally to the rear at his maximum height, such that their horizontal velocity is 0 relative to the ground. Very interesting. So what that means is, because he was moving forwards, right, in this phase, the halteres have a positive forward horizontal velocity, but it's saying that he throws them in the backwards direction relative to himself with just enough speed so that the sandbags to an observer look like they're stationary. Does that make sense?
Yes.
Yeah. So that's basically their indirect way of telling you how fast they're being thrown backwards. So yeah, let's figure out how to actually set this thing up, because I'm not totally sure off the top of my head. But I think that from part A, the regular jump, this thing should tell you, this equation right here should tell you this is just going to be T max over 2, right? So if T max, if T of the entire trip was just called, let's call that delta T, this would just be delta T over 2, right? Because that's the tallest point. And what else do we need to know? At this point, you can figure out what their... Okay, so at this point, their Vx, because that's like constant, right? Actually, I'm not even sure if you need this right now. Let me think. Maybe not. Okay, I've got it. So the conservation of energy at this particular point where they're doing this throw, right? This is basically saying Pi is equal to P final. And we're going to work from the reference frame of the observer, okay? So their initial momentum was basically mass of the person. What symbol did I use there? Okay, so I'm just going to use regular mass for mass of the person plus mass of the hectare thing times Vx is equal to, and keep in mind that velocity initially, you have to remember both masses, right? You got to remember that. But that's going to be equal to mass of the hectare thing times velocity of the hectare plus mass of the person times velocity of the, I don't know, let's call it V nu. Or maybe let's call it Vx2. And what else we know is that because the problem is telling us that the horizontal velocity relative to the ground is 0, this term just goes away. So that's really nice and simple. So all you got to do at this point is solve for Vx2, right? Simple enough. Once you know Vx2, well, you know that it took delta t over 2. Like, you know how far distance he's gone already, because that's just v of x times delta t over 2, right? But then for the second half of the phase, which takes another delta t over 2, he's just going at a boosted velocity. So it just looks like Vx original times delta t over 2 plus Vx2 times delta t over 2. And that's going to be your final distance that he makes it using the boost. Does that make sense?
So far, so good.
Yeah. And then I think the problem is asking you what distance the Haltiers would add to his range. So, like, once you find this total distance, just subtract out whatever this used to be. And I hope that makes enough sense. Right? Okay. So now we're getting to the end of the medium problems. And it's saying particle A and particle B are held together with a compressed spring between them. Okay. So this is mass A, and this is mass B. When they are released, the spring pushes them apart, and they fly off in opposite directions, free of the spring. Okay, so we know that mass A is equal to 4 times mass B. Okay, in that case, I might just rewrite this as 4 mass B to reduce the number of unknowns that I have. And the energy stored in the spring was, okay, like 90 or 100 joules or whatever, right? So that's going to call that U in the spring was equal to just some given number, whatever. So we're saying that the spring has negligible mass, and that all its stored energy is transferred to the particles, okay? Okay, this problem is basically saying now we have a situation where we have both conservation of momentum and energy. And we're going to show that that's enough to sort of let us know everything about the situation. So, okay, this is very cool. Excuse me. So when everything's still, right, what's the momentum of the system? It's kind of a trick question, but...
Nothing.
Exactly, nothing, right? So P initial is 0. For this particular problem, I'm going to try to write things in as mechanical way as possible, right? And because there's no like net force in the system, what is PF? Like of the total system?
Same thing, because it's still not moving.
I agree. It's still, well, they're both moving, right? It's just
But,
that
like,
because it initially was 0, by conservation of momentum, it's still got to be 0. Because PI is equal to PF in the absence of, for a total system, I should say. For a total system, the initial and final momentums have got to be the same. That's what conservation of momentum means, right? Like, if between you and me, we like pushed each other off, like we were still for a moment, and then we just pushed against each other, like one of us might weigh more than the other, so one of us might move faster than the other, but our total momentums before and after have both got to be 0. right? That's basically what's happening here. Like the spring is just a convenient way of saying these two things are pushing off each other, right? But okay. So what this is basically saying is, excuse me, mass of A. Okay, so the fact that the final momentum is equal to 0, that's basically saying, if we choose this to be our positive direction, this is basically saying mass B times velocity B plus mass A times velocity of A. I'm going to choose this value to be positive and then represent the fact that it's going left with a minus sign here, okay? Like sometimes I'm all over the place with this, and you just gotta, you always just gotta sanity check yourself what the signs ought to look like. But this is basically saying that this is 0, right? So that mass B VB is equal to MA VA. And we know that mass of A was just 4 times the mass of B, right? So this basically gives us a relation between VB and VA. But this is only one equation so far, so with 2 unknowns, we can't quite solve it yet. Oh, I'm sorry. In fact, we have in fact 3 unknowns because mass B is also not known. So we got to come up with more equations, right? We gotta get ourselves some more information. So what else can we say? Energy is conserved. So K, I guess I'll call it K initial plus potential initial is equal to K final plus U final. And it's not initially moving, right? So this is 0. And this value is the energy from the spring. That's this value right here. And then there's no energy once it gets released. So this is basically saying potential energy of the spring is equal to the total kinetic energy of both particles. So that's basically saying the potential energy of the spring is equal to 1/2 MA VA squared plus 1/2 MB VB squared. So far, so good?
Yes.
Okay. So what am I missing here? We've got 1 equation, and we've got 2 equations. And how many unknowns do we have? Is it still just 3? Because MA is again 4 MB. So it looks to me like we're missing something. We got to figure out how. We got to figure out maybe 1 more equation that we can write down. Or maybe I'm just missing something with. Maybe there's a relation that I'm not seeing. Okay, when they're released, spring pushes them apart, flying in opposite directions. Mass of A is 4 times. Spring energy stored is 90 or 100. Assume the spring has. Okay. Kinetic energy. Oh, hold on. They're not asking us. We might be able to get away without having to solve for everything, right? Because they're asking us basically what these 2 terms are, which is basically saying like breaking these down. Excuse me. What kind of breakdown or partitioning does the energy have, right? Like this is the total energy. Like what's the fraction that goes into mass 1 and what's the fraction that goes into mass 2? So yeah, I think this is actually not so bad, right? Because if we just rewrite VA as, like, my point is we never actually have to solve for mass B, which you'll see in just a second. So let's basically solve for VA, right? Solve for VA in terms of VB, and you should see that the MBs just kind of cancel out, right? You with me so far?
No.
No? Okay.
The
Uh,
MBs canceling out.
Yeah, remember that this equation right here was MBVB minus MAVA is equal to 0, right? This is just conservation of momentum. And
Okay,
this
okay.
used to be MA, but I'm just rewriting it as 4MB because that's what the problem told us. That
Right,
it's
right,
just 4 times the mass, right?
okay.
So just
With you
cross
again.
off MB from both sides, and you can see that really conservation of momentum gave us this relation between VB and VA. Right? Because one was 4 times as massive, the other one must have 4 times the speed, is essentially what this is saying for momentum conservation to work out. That seems kind of believable, right? Because like in momentum is equal to mass times velocity, mass and velocity are kind of on equal footing. So if one of them gets a multiplier of 4, the other one has to get like a multiplier of 1/4. Does that make sense?
Yes.
Yeah. So yeah, that's this relation between VB and VA. But now the idea is, well, why don't we just solve for VA and go ahead and plug that in right over here? And you should be able to see that this term right here becomes something like C times MB VB squared. And then this term over here is just 1/2 MB VB squared. And I'm telling you that you can just figure out what C is because this is just going to be a mishmash of constants, right? Because this 4 is going to come in here once you solve for it and square it. And then there's a 1/2 and there's a 4 already. So basically just multiply all the constants together to find what C is. I'm not going to do that for. Yeah, I'll leave that to the students. But the point is, right? At this point, this is a contribution of 1/2 MB VB squared, and this is a contribution of C times MB VB squared. Yeah? And it's just asking you, at this point, if this is all equal to like 100 joules or whatever, it's basically saying you can just tell by fractions what each relative like amount is. You see what I'm saying?
Yeah.
Because this is exactly the same between the two of them. So to figure out the fractions, you just have to look at the coefficients, right? Like if this C was like, I don't know, 2, if it came out to be like 2, then this would be like 2 MBVB squared plus 1/2 MBVB squared. So then this would become like 2 out of 2.5, and this would become 0.5 out of 2.5, where 2.5 is just the sum of whatever these things were, right? So like if C was equal to 2, which I don't know off my top, I just guessed. But yeah, it's basically asking you to find the fraction. Seem reasonable enough?
Yes.
Very good. Okay. So now we're on to the hard questions, right?
Yes.
Okay. Yeah, by the way, I just wanted to say that for anybody listening, I try to do a session like this every week. But yeah, I never know how to ask this politely, so I'll just ask it. But please, if this helps you, please like, subscribe, or ask a comment or clarification question in the comments, because I'm doing this for free because I enjoy teaching math and physics, and my hope is that as time goes on, I'll be able to reach out to more and more people, and engaging with the video is one way to help more students find what I do. All right, so back to the problem. Okay, it's saying that we have, so this is hard, right? Hard problem 1. It's basically saying that we have these sort of 3 masses that initially are at rest, and then an explosion happens. So let me ask you this. If they're at rest first, and then they're suddenly moving, it's like, wait a minute, isn't that kind of crazy? Because at first there's no kinetic energy, but later on there's kinetic energy. How can that be? It's not necessarily a trick question. It's just a good thing to remind yourself of.
The potential energy
Yes.
going away?
Yes,
I mean,
actually.
kinetic?
Exactly. There's latent potential energy in the chemicals that form the explosion, right? So the idea is the explosion essentially converts potential energy into kinetic energy, and probably also heat too while it's at it, but it imparts a bunch of energy to the pieces, and that's how they get them moving, right? It's basically saying, like, it's sort of the explosion is doing work and getting the pieces to move. It's just something I want to bring up because every now and then, if you don't explicitly hear someone mention this, you might on a test be like, wait a minute, why isn't energy being conserved in this situation? Well, it is. You just got to remember that there's energy in the explosion too. Anyways, that brief aside, after the explosion, okay, it's saying one piece is mass m and it's moving directly to the left. That's the negative x direction. Okay, let's say that this is positive x and this is positive y. Right, a second piece moves the same velocity. Okay, so that's velocity v. And then a second piece with mass m and v goes down here. And the last mass has 3m. And it's got to be moving somewhere vaguely here. You can kind of see just from conservation of momentum that, you know, because this has a left component and this has a down component, this one's kind of got to be upwards and to the right. Does that make sense?
Yes.
Yeah. By symmetry, right? Because this is in the negative x direction, like exactly in the negative x, and this is exactly in the negative y, and the masses are the same, you should be able to just right away figure out what this angle is right here. Do you see the symmetry?
I see the symmetry, but I don't
Like,
correlate how.
yeah, I can maybe just make this a little bit more explicit, right? It's basically saying that, how do I put it? This, whatever this velocity is at the end, right? This is called like v of, I don't know what you want to call it, v of v2. It's got to have an x component and a y component, right? And because of conservation of momentum, this mv and this one had a momentum of mv downwards, and this one had a momentum of mv leftwards, right? So it's pretty clear that whatever this v2 is, its horizontal and vertical components of momentum have got to be equal in value because this and this are equal.
Yeah.
So that right away should be able to tell you what the angle is, right? And I'm not going to say it out loud, but does it seem relatively clear?
Yeah.
Yeah, very good. So they chose the numbers really nicely. And note that it matters that this m, this m and this mv and this mv are equal to each other is basically all that you need to know that the angle, well, is going to be what it is. Just think it through. I don't want to say it out loud. But noticeably that it didn't matter whether this was the 3m or 4m or 5m. Just the fact that these were equal to each other, and, you know, one was perfectly in the negative x, the other was perfectly in negative y, is enough to guarantee us what this angle is. We don't even have to know what this mass is. Okay, that aside, what is the magnitude of the velocity of the third piece? So for this problem, it's similar to before. It's just that now that momentum is conserved in each independent direction as well. So in the x direction, momentum x in the I direction initial is equal to 0, right? Because initially nothing's moving. And that's got to be equal to conservation of momentum x final, which is equal to, I think this one over here is minus mv, that's from the mass going leftwards, plus 3m, this is the mass of 3, times v2 cos theta, right? And like I said earlier, because it had this nice symmetry to it, you can figure out what this theta is immediately. And then at this point, it should just be very easy solving for whatever v2 is. Right, because 0 is equal to all this stuff. So just solve for v2. But if you did not see the symmetry with the theta and wanted to go through the full problem, you would basically do something incredibly similar with yi is equal to 0 is equal to yf. And this is equal to minus mv because of this thing going downwards, right? Plus 3m v2 sine theta. So at this point, it's 2 equations and 2 unknowns. And if you did not know what theta was because, you know, maybe let's say the problem was a little bit different with one of the masses being a little bit larger than the other over here, so that this theta would not have been as obvious from symmetry. By the way, do you know how to solve an equation a system of equations that looks like this when you have cosine thetas involved
Yeah, I think so.
and sine
You
theta?
just- Yeah.
Yeah, I mean, you can always take the arc cosine and arc sine, right? But the way I would do it is isolate this term, like move this stuff to the other side, and do the same over with this bottom equation, and square them both so that you can take advantage of the cosine squared plus sine squared identity is equal to 1 and just get rid of theta.
Oh, I would not have done that.
Yeah, it's one of the classic tricks you pick up in intro physics, and it's a lot nicer than having to deal with an arc sine or arc cosine, right? But yeah, I think from here it should be reasonably simple to solve for v2. Right, one way or the other. You can either use both equations to solve for it, or again, you can just remember that theta should be very I'm not going to say, maybe I shouldn't say obvious, but it should be findable just by the symmetry of the problem without having to even think about numbers. Feel good about this one?
Pretty good.
Okay, and I think we're at the last one today. This is like some ball coming in, right? And it's coming in at some VI, and it's got some mass M. And this little like gun coil thing, it's got a spring on the inside that'll compress, but it's also on ice, so that like the reason this problem is kind of complicated is because when this thing comes in, it's not only going to be its kinetic energy like gets soaked up by two things. One is it compresses the spring, so some of its potential energy is converted into the spring's potential. And two is because now this thing is going to move a little bit on the ice, which means that it sort of picks up some kinetic energy. So let's say that VI is the velocity of the ball coming in. And let's say VF is the velocity of the gun at the end, right? And one of the things to notice, like one of the, I would say, key insights for this problem is that at the very end, when the ball is compressed fully, remember that it's not moving at speed 0 relative to the observer. It's also moving at speed VF. Does that make sense?
Yeah.
Yeah. This is one of those things that's really, really easy to overlook because, you know, you think to yourself that it's coiled up all the way. It's, you know, the spring is no longer like springing, I guess. It's really, really easy to forget and just say that, oh, okay, the final velocity of this ball is 0. No, because it's moving, even though the spring is coiled up, right? It's still inside the gun. So now it's just moving in lockstep with the gun. And they both have the same final velocity. Okay, so this problem is just a little bit complicated because, again, it's both conservation of energy and momentum. But okay, so Ki plus Ui is equal to Kf plus UF. This is from energy, right? And we're assuming nothing gets lost. So kinetic energy, potential energy initial is 0, but everything else is non-zero. So kinetic energy initial is 1/2 m vi squared. They tell you what little m is, right? That's the ball. They also tell you big M is the mass of the gun. Maybe I'll call that big M2 just to make it clear. Right? But that's going to be equal to 1/2 times M times VF squared plus 1/2 times big M2 times VF squared plus 1/2. Do they tell you the spring constant? What is the speed of the spring gun?
We do not have a spring constant.
We do not have a spring constant. Interesting. Okay. I guess it's probable that, let's maybe just call this mu of the spring then, okay? It's possible that we don't even need it. So that was energy conservation. Everything over here feel good so far?
Think so.
Okay. Please do speak up if anything is uncomfortable, right? But then conservation of momentum is basically saying, all right, the momentum initial was, it's annoying that everything's going to the left, but for consistency, I will say that, you know what, let's just call to the left the positive direction for this problem. Okay? because everything's moving to the left. I don't want to put negative signs everywhere. Sound good?
Gotcha.
Okay. So delta conservation of momentum tells us that m times vi is equal to, I guess it's just going to be m times v final plus big M2 times v final. And yeah, what's odd at this point is, what is the speed of the spring gun after the ball stops in the barrel? So it's basically asking us, what is VF, right? And let's do a quick intake. We know what VI is, right? Because it tells us. Yep. So
Right.
It seems to me that, in fact, these equations look kind of nasty, but really our only unknowns are VF and US. Right? It seems to me that everything else is known. Yeah?
And you solve, right?
Yeah, exactly. Solve. I was actually a little bit confused because it seemed complicated, but turns out it's, well, it looks a little nasty, but it's really not that bad. Just solve for VF and US. And once you have that, okay, so one of the things they asked was VF. The other thing they're asking is the initial kinetic energy of the ball. What fraction of the initial kinetic energy of the ball is stored in the spring? Okay, so then you just figure out what US is and take the fraction out of the total initial kinetic. And yeah, that's all there is to it. Okay, any last questions? Do you think we should go over the like that 1 or 2 easy problems that were weirdly card, or?
Yeah.
Yeah?
Let's do, I think it was 6, right?
6. Yeah. It was it was surprisingly obnoxious. Or maybe I'm just missing something. But yeah, so that problem was 6 on the easy. So that's like 3 blocks. So L, C, and R. And okay, so they give you some masses, like let's call this big M1 and little M2 and little M2. So like left and right are the same mass. And what it tells you is that the rocket consists of a central block, blah, blah, blah. So there's like little explosives wedged here and wedged here. The first one explodes, sending this block off and that block off, and these 2 blocks off together, right? But the issue is that if this is V1 and this is V2, they don't tell you the individual velocities. They just tell you that V2 minus V1 is equal to like some value, let's call it 3 meters a second, okay? And then, okay, so then these things are, we don't really have conservation of energy because we don't know the amount of potential in the explosive. So this problem is purely conservation of momentum. And what we can say is that from the reference frame of the observer stationary on the ground, this looks to me like, how do we want to write this? So if this is the positive x direction, this is basically just saying M1 plus M2 times V2 is equal to, excuse me, or I guess let's write it this way. Delta, sorry, the change in the momentum is 0, right? So momentum initial total is equal to momentum final total. And because the initial momentum is 0, then the sum of all the pieces in the final have also got to be equal to 0. So M2 V2 is equal to 0, with the understanding that V2 is in the negative x direction. So at this point, this is, I think, 2 equations and 3 unknowns. So we can't quite solve for anything just yet. Wait a minute. Is this, how many unknowns is this? Wait, I'm a little bit confused. It looks like we can just solve for it. Am I going crazy?
To pull out 2. No, I think, yeah, how? Whoa, I don't see it.
Sorry, let me just remind ourselves what we do know and what we don't know. We do know all the masses, right?
Yep.
We just don't know the velocities. So this is two equations and two unknowns, right? Am I going crazy?
There's only one.
What's up?
Hold on.
Yeah, I was going crazy. I'm going crazy right now because earlier I thought that you couldn't solve, but right now I'm seeing no reason why you can't. It's like V2 and V1 are unknown, but everything else is known, right? Yeah. Yeah, I think that's right. Yeah, I guess I was not really paying attention earlier because I just solved for everything symbolically and did not realize that I had actually fully solved it. But you good so far? Right, just solve for V2 or V1. And then after like a second or something, you have these two things moving to the right, but then another explosion happens, and now the little block shoots off with some even greater speed, and the big block, it's actually not very easy to tell right away whether it's going left or right. So let's say that it's going to the right. Let's call that V3, and let's call this one V4. And if it turns out that it gets wrong, then this V3 will just be negative, right? That means it'll be in the opposite direction. So yeah, it's basically the exact same idea with V4 minus V3 is equal to whatever they say, like 3 meters a second or whatever. And then the conservation of energy, like the equivalent of the second equation, is basically saying that, well, this time around, it's not equal to 0 because there is some initial momentum. But the initial momentum is going to be just m1 plus m2 times v2 from the previous system of equations. And that's going to be equal to, so this was big M1, right? And this was small M2. Yeah. M1 times V3 plus M2 times V4. So this is another set of two equations. You can figure out what V2 was from the previous two equations. And then, yeah, you can just solve for V3 and V4. Kind of a pain, right? But conceptually, hopefully it makes sense after it's been broken down.
Yeah.
I was a little bit confused because I saw these problems and saw that the, relative velocity between the second explosion and relative velocity right after the first explosion were the same value. So I was looking for some symmetry in this problem. Like, I was hoping that the block would just, after these two explosions, the middle block would just be perfectly still.
Yeah, that's what I was thinking.
Right? But I don't think you can immediately tell that just from the relative explosions, unfortunately. I think the relative velocity information is just a little bit too vague. And I plugged these numbers into a linear equation solver because I didn't want to do it by hand. And I was getting not terrible, but not particularly nice numbers either. And I was getting that the middle block was still moving at the end. But once you've solved for all four velocities, right, those are sort of your unknowns, yeah. V1, V2, V3, and V4, you can just use that information to figure out, figure out how far block one has moved. How far the middle block moves in the first phase of the problem, and then how far it moves up to the second phase, because you know the times, right?
Right.
And yeah, that's basically all you need. Yeah, I was really hoping for something elegant. I just wasn't seeing it. But yeah, any other questions on this one?
I think I'm good.
Okay. Well, right. I guess that wraps things up for tonight. For any viewers, if this helps you out, please remember to, like, subscribe, or leave a comment, or otherwise share to let other students know how to find my stuff and see what I do. I'm happy to do one of these problem sessions for basically any class. You just have to ask. You can find my email on the side of the screen. Alrighty.